Now we're going to dive into IP addresses and how they separate networks. IP addresses can be leased out to devices just like how mobile network companies like T-Mobile or Verizon lease out phone numbers to our cell phones. Your SIM card is your phone. In your phone holds your phone number lease from your mobile phone company. In the same fashion, a network interface card in your PC or laptop holds your device's IP lease or static IP address. A DHCP server or servers are used to lease out IP addresses for a network. So these servers can be an actual server or a process running on a router. Remember how our PDU had to be changed to binary to be transmitted between devices in a physical layer? Well, IP addresses can also be read in binary. To find how to translate IP addresses to binary, we have to understand how binary works. Think of binary for IP addresses as being split into 8 lanes. Each lane represents the number 2 raised to the power of a number between 0 and 7. So 2 raised to the power of 0 is 1, 2 raised to the power of 1 is 2, 2 raised to the power of 2 is 4, 2 raised to the power of 3 is 8, so on. So notice how it's basically doubling each number from the lane before. So 1, 1 is 2, 2 and 2 is 4, 4 and 4 is 8, so on. So let's look at our IP of 192.168.1.20 and break it down. We'll start with the first section of our IP. This section is also known as an octet or group of 8, since the first number is made up of the 8 binary lanes. Here we see what number each of the 8 lanes represent. To reach 192, we need to turn on certain numbers of the lane. Turning on 128 and 64 will equal 192. So this is how we get 192 in octet 1. We do the same process for octet 2, octet 3, and octet 4. If all the bits of an octet are turned on, the highest number you can get is 255. So the last IP you could ever have in IP version 4, which is the one we're talking about right now, is 255.255.255.255. Here we can see how the 255 is made up of all ones or turned on bits, right? So 1 plus 2 plus 3 all the way, right? You get 255. Same goes for octet 2, 3, and 4. So to separate or split networks, we use network masks. So let's look at our 192.168.1.20 IP, right? We'll be able to see what network it belongs to based on a mask. Here is our IP in binary for each of the 4 octets, right? So they're all here. And here's the mask we're going to use so that we can tell which portion of the IP belongs to the network and which portion of the IP can be divvied up to different host devices. You can see the mask octets represented here in binary. So all ones for 255, all ones 255, all ones for 255, and then 0 is all zeros. So the way the mask works is that for every mask bit that is on, it stops the IP bit from being able to change. So these IP octets are blocked by the mask and can't change, meaning they belong to the network portion of the IP address. On the other hand, every mask bit that is turned off here means that the mask bit is open and the IP bit is allowed to change. So these are all allowed to change. Meaning this portion of the IP is the host portion of the IP address, right? So in this case, the last octet is fully open and can be any number between 0 and 255. This mask has 24 bits turned on. So there's 24 ones in this mask. So we can write this out in shorthand. Instead of writing out all the octets as binary, we can use /24 because there's 24 mask bits that are on. So together, the IP would be 192.168.1.20/24. So this notation tells us our IP, our mask, and what portion of the IP belongs to the network, and which portion belongs to be divvied up to the host devices. So the host portion. Let's dive deeper into our IP addresses and see what else we can learn from it. For example, we know it belongs to one network. I'll show you how we know that a little later. We know every network needs a network address. A network address is an overall address for a set of IPs in a network. The network address is usually the first open address in a network. In this case, that would be 192.168.1.0. Next, we have a group of available open addresses. These addresses, these are addresses that start in a range based on the host portion of the IP address, the portion not blocked up by the mask, right? So this portion here, not blocked by the mask, that can be assigned to host devices. Meaning we can't use .0 because that one is assigned to the network address. So all the ones that are available would be .1 and on, right, as of right now. Finally, we have one broadcast address. So the broadcast address is always the last open address in a network range. So this IP address is used to send messages to all other IPs in a network. So one example we saw of this was the broadcasting of ARP requests, which we took a look at back at earlier. So in that case, our laptop was sending out a broadcast to find a MAC address of an IP we had. It did that by sending a broadcast using the broadcast IP address, which in this case is 192.168.1.255. So let's break down how to find each of these three pieces of information from just our IP and the subnet mask. First step is to write out the decimal notation of the mask. So 24 bits on, we know that's 255.255.255.0. In step 2, we're going to find a network address. We do that by first carrying down the IP octet of our IP each time the mask octet is 255. So this is 255, so we're going to carry down 192. This is 255, we're going to carry down 168. This is 255, we're going to carry down the 1, right? And so basically, whenever the mask octet here, like right here, 0, we're going to carry down the 0 because that means all the bits in that octet are open, meaning this portion of the IP belongs to the hosts, and it can be any number between 0 and 255. And remember that the network IP is the first open IP in a network range. The first IP here would be 192.168.1.0, making that the network address. In step 3, we're going to find a broadcast address. We do that by finding the last open IP in the network range, right? So the last one. So this was the first one. Now this is the last. We do that by finding the last one in the range, and we know that the network range starts from 192.168.1.0 because our mask revealed the network address and the first open address, right here. And we know that if all the bits were on in the last octet, which is the only open octet based on the mask, it would be 255, right? Because all bits turned on for an octet is 255. So that means the range is 192.168.1.0 to 192.168.1.255, with this one being the last open IP address, making it the broadcast address. Finally, in step 4, we're going to find the available IP addresses that can be assigned to devices. So we do that by looking at how many open IPs there are between a network address and a broadcast address, right? In this case, there are 256 open addresses because you include 0 in your count. Then we subtract the one network address, which can't be assigned to a host device because it represents the network. And then we have the one broadcast address, which also can't be assigned to a host device because all devices use that to send out broadcasts. So this leaves us with 254 available IP addresses that can be assigned and divvied out to other end user devices or host devices like switches and routers. So what about dividing networks into smaller groups of addresses? Like maybe you have one company network and want to divide into departments. One network for marketing and sales with limited access to resources, and one network for IT, which has more access. That's where subnetting comes in. We can split a network into smaller subnets by simply changing the mask. Because remember, a mask tells us which portion of an IP belongs to the network and which portion can be divvied up to host devices. That's why those masks are called subnet masks. So we know that /24 means there are 256 open addresses. And by subtracting the required network address and broadcast address, we get 254 available host addresses, available addresses for host devices, right? Now let's say what happens if we add one more bit to the subnet mask, which means that we're essentially borrowing one bit from the host portion of the network IP address and adding it to the network portion, right? So we're taking it from the host portion and giving it to the network. So with the mask notation, we can use this shortcut to find the open and available IP addresses. We know that the max possible bits is 32, right? How do we know that? We know that because if all the octets had ones turned on and each octet has 8 bits, 8 times 4, because there's 4 octets, is 32. So if everything was on and it was 255.255.255.255, we would have 32 bits, right? So that means there's also 32 possible bits that could be open. So we know there's 32 possible bits. So since we know the max possible bits is 32, if we subtract the bits that our mask is using, which is the 25 now, right? Because we borrowed one bit for the mask. So we have 25 mask bits. We get the number 7, right? So the max possible here is now 7 because there was 32 possible ones. We used up 25, so there's 7 left. So those 7 bits are available for the host portion of the IP address, the network address. So each of those 7 bits have 2 possible outcomes, right? One being 1 or one being 0. So either on or off. So if we raise 2 to the number of 7, we get 128 open addresses for the host portion. All right, so these are the 128 possible addresses that can be divvied out right now. But we do have to subtract the network portion, the network address, and broadcast address. So that leaves us with 126 available open addresses that can be divvied out to different devices. So if we divide 256 by the 128 open addresses that we started with, we'll get the answer as to how many subnets, each with 128 addresses, make up this network, right? Since we get 2 subnets, we know each of these are going to have 126 available open addresses that can be divvied out, right? Because one of them has to be the host, one of them has to be the broadcast, which means there's 126 left in each subnet. So let's take a look at the new /25 subnet mask a little deeper and see how it separates the network. We have our IP and subnet mask, and here we have them written out as 4 octets, right? We've seen this process before with the /24 mask, but now this is /25. Whenever a mask bit is on, the portion of the network address can't be changed, as we discussed before. And notice how we have 1 extra bit here in the mask that goes into the last binary lane of the last octet, right? So this last octet, there's the 8 lanes. This mask is borrowing this lane of this octet. So remember that for each binary lane, there's 8 of them, and it's represented by 2 to the power of a number, right? So 2 to the power of 0, 2 to the power of 1, 2, 3, 4, 5, 6, 7. So 2 to the power 7 represents what this number here would be. So this mask number, 2 to the power 7 is 128. That's why we have 128 right here. So this means the last octet is only partially open and can be any number between 0 and 127, because we're not including 128, because 128 would be the start of the next network, so the second subnet. So because this mask has 25 bits that are turned on, represented by the ones right here, the shorthand is noted as /25, because it's 25 turn on bits in this mask. Meaning the full notation is 192.168.1.20/25.